Okay, again, this is still deterministic situations, right? And as you see here, I think I better take this. They are still deterministic, but the periodic functions, I talk about Fourier series. In page 18 is all coming back to complete the Fourier series. And all three different types, I'm going to briefly again touch to it. Then I'll assign to verify all three expressions like classical Fourier series, polar forms, exponential forms is all same. Then I'll give you all the hint, then you can complete. Then mid next week, then I'll assign the regular homework. So that's what I'm going to do. Okay, this is the almost periodic data. Almost periodic, not quite periodic. And the expression is x is equal to the summation of xn amplitude sine 2 pi fnt plus theta n. Here, almost periodic has one condition. Fn over Fm shouldn't be the rational number. The question is, what's the rational number? Anybody can tell? What's a rational number? Let me write it down for you. Rational number. Rational. You might forget this. This is any number. Any number that can be expressed as a quotient. A over B, where A and B are integer. And also B is not equal to 0, which is the definition of a rational number. So here, for example, in this expression here, this is a 2, 3, 7. So any quotient using 2, 3, 7, this is integer over integer. If I say 2 over 3, or 2 over 7, or 3 over 7, that's all integer value, then that's a rational number. Then this means this is a periodic data, right? But this one is almost periodic. Almost periodic means it's really non-periodic. So because of what? Because of square root of 50. So whether this is, which is not integer. So if you take this guy as A over B or A over C, so that fraction is not the fraction of integers, so that's almost periodic. So you can tell this is almost periodic, and this is of course periodic. So in general equations, this ratio Fn and Fm, which is really ratio of this term, 2 pi at the top or at the bottom, it cancels up. So you can just think as a ratio of 2 value Fn over Fn. Clear? Okay. And that's almost a periodic. And the transient phenomena. When you hear about the transient, that's really the non-periodic data. So this first example, I think we maybe showed before. I'm not sure. The expression, the equation expression, t is greater or equal to 0. This is something like the shock absorber. Shock absorber is you just release it and slowly comes down here. This is a time domain function, and if you throw into frequency domain function, it goes like this. Right now this is introductory section, so eventually, of course, you want to really get the plot sometime, deriving the equation forms of frequency domain functions, things like that. And this is x is equal to, this is typical, the transient, the time history, you can say. And x is equal to a times e to the minus st times cosine bt, which is really, think about, you can think about the, something like this. So mass, damper, spring. This is the principal direction of motion. Then you can add the forcing function. It's a typical 1 degrees of freedom, damper the oscillator. And usually you can say this is a discrete component, saying spring and damper, or any really material. You can think of this as a material, then can have a mass, and also you can model this guy like this. What does it mean? Vibrations. When you give initial excitation, eventually it stops. Motion stops due to the damping. That's what exactly this is. This is cosine e to the minus st. So if you just tap this oscillator, tap it, then it has that case is a cosine oscillator. Then eventually it just die out because of the damping in the system. Whether like this or this, it eventually dies out. So so this decay rate is something like e to the minus st. Okay, so typical transient, because it doesn't repeat. That's a transient phenomena. Any shock problem, any impact problem, the response is all the transient. Okay? And as you look at, here is a cosine function. So cosine has the frequency, right? Whether it decays or not, cosine has frequency around a particular frequency, and you can tell that it has a peak in it. This is a frequency versus the amplitude. That particular frequency is what the B is 2 pi f, or B is like omega. Okay? Particular. And this is a square. It's typical square pulse. That's like a pulse type. And to get the pulse, you think about such a pulse, to simulate, to generate such a pulse, you need many different frequency components. Then you should be able to really simulate such a square pulse. So you need more than just one frequency component. Could be a lot more. It has only, as a sample 3, could be more and more. Okay, so this is not repeatable. There is no period here, and this is typical to transient phenomena. And the Fourier transform, as I mentioned here, when you get to Fourier transform around the page 20 or 22, then you will see. I'll give you also a complete review of Fourier transforms. Fourier series, Fourier transform is really foundation of dynamics and the vibrations and also random processes and all. So I kind of insisting you must know. 80% no, 90% no, 100% you have to know before you do the deterministic process or random process, okay? Now, slowly getting into the random data. So I give you some example about ocean wave motions. If you measure the height, or this is the one sample record of a thermal noise generator signal. Then as you see here, all this signal is a measurement at different time at the particular location of a sensor. It's not identical at all. So it starts from here coming down. This case is from down. This. So as you look at, nothing is the same. So such a function, such an individual function, is called the sample function, or the sample record. Record of function is individual functions. Okay. So or stochastic function. That's fine. Stochastic. The record is also same. But random process or stochastic process is, when you say about the process, meaning is slightly different. When you talk about the function and the record, you are talking about the one-time history. That's a one record, okay? It's not the multiple record. When you say about the process, stochastic process or random process, you are talking about the collection of individual record. It's like a family of record. So in the random process, we are dealing with the family of a sample record. Very important, because each individual record is all independent each other. Nothing is the same. But if you look at the statistical sense as a collection of a sample record, it has a meaning in there. So you have to bring the statistical concept and statistical analysis. So the OSE, I think it's mechanical engineering or aeronautical, is all the same. To taking the statistical course, at least one is mandatory. It's not the option. If it's option, there's something wrong. Even in the graduate studies, undergraduate, of course, you took the statistics course, I bet, or probability course. It's all the same. Then statistics is a backbone or core of a stochastic process, by the way. But here, I'm just giving you all the ingredient on statistics to be explain the random processes, okay? So he said here, random processes or stochastic process, a collection or ensemble is the same word, collection, family, ensemble of all possible sample functions is called the stochastic process. It's just a family of the same type of the signatures. Now slowly coming into the ensemble. Ensemble is a family. Random processes is all same. So put the typical notation is put the parenthesis. That's a typical notations, okay? When you hear about the X, that's the processes. And the XT is a sample record, it's a different. And this is ensemble, typical name ensemble. This is processes, more than one. And in this particular sample, the collection of sample records has 1, 2, 3, 4. And here, by looking at this, I can explain the definition of a stationary process. Stationary process. Stationary. Stationary process. This stationary process, listen carefully, this is a measurement at different time, okay? The same kind of the phenomena, something like, could it be turbulent pressure at the tip of the wing when they fly at 10 a.m. in the morning, and next day they have a similar condition and they record all that pressure. It's another time. So by looking at this, let's say for record here, I'm taking the amplitude at T1 here, and here amplitude at T1 for the second record, amplitude for at the same time for the third record, at the same time this is at T1 time for the record. Then if you take a mean, you can measure 10, 20, 30 different record, then you can determine the mean value. One of the first statistical value is a mean value. Typical value. Typical, called usually mu x, or same thing, mean value, or notation wise you may saw all this. Mu x is mean of x. E means expected value. Expected, which is a mean, same meaning. Expected value of xt, which is mean. So if you take if you compute the mean value is one of the statistical parameter at time t1 and at time t2, which is a t1 plus the tau, it has a, let's say, distance time duration is tau, so this guy is, let's say, t2, then you can, using that, the point, peak point, then you can compute the mean value. So you can compute the mean value in this case. Mean value x at t is equal to t1. So I'm going to say this is, let's say, a mean value. So if I say, okay, at t is equal to t1 plus tau, or you can say this is equal to, at time t2, let's say is equal to b. Okay, if a is equal to b, in other words, if the mean value at any time in the ensemble, if it is the same, then you can call that signature as stationary process. Makes sense? If A is equal to B, then xt is the stationary process. I'm just showing a little bit ahead of the time. So, which is called the ensemble. This is ensemble. If A and B is the same, then that is called the stationary process. Stationary process. Let's see. So in terms of the equations now, let's look at the equation set. So equation set. Stationary process, you got that. But stationary process. So ensemble average for non-stationary and stationary data. So we define the stationary process. Then how you can define the non-stationary process? If the signature is not stationary, then the signature should be the non-stationary. That's about it. In the random process, you have two. One case is stationary. If it's not, the other side is non-stationary. So over here, this is a few kind of the basics and important statistical parameter. I talk about the mean value. So mean value at time t1. Visualize the slide just before. Time t1 at a particular time. In the time axis, if I say mu x at time t1 is equal to different notation but same meaning, expected value of x at time t1, okay, you could have many collection of many records, right? I could say n approach to infinity, but nothing is infinity in the world. Everything is finite. That's what you're learning about the finite element approach. Finite element is a finite. It's not the infinite. Finite element approach. then you have to discuss about the convergence criteria. Why? Because the element, number of element has a finite number. So here, so n, I could say in engineering sense, n is large number of record. Okay, in the ensemble, large number. That's all we can handle as an engineer. Is summation of all the record at all the peak at time t1. That's what this summation is for. Then divided by the number of the record, right? So this is the mean value. Mean value at time t1, mean value at time t2, mean value at time t3, t1, t2, t3, that could go not infinite, large. Then if the value at ti is a kind of a constant, then you can say stationary process. Then you could ask a question, is it just a one parameter mean? No. It really should span for set of the parameters. Another important parameter is the mean square value. So there is a few parameters. One is mu x at time ti. The next one is mean square value. Anybody heard about the mean square value? This is simply notations at time t1. So ti, let's say, I is going to be arbitrarily time, arbitrarily time, any time. That's what I'm saying. Any time. So mean square value. This mean square value is, you can write this guy as shown over there, x square t1. This is a mean square value. If you take a square root of a mean square value, what can you say? This is mean square value. Mean square. Mean square value. Mean square value. If you take a square root of this guy, what do you call this? Square root of mean of square. This is root mean square. Root mean square value, or RMS value. So alternate currents, the current, you have to deal with RMS value because it's always changing. So as you see here, this is expected value of x squared at time t1. T1 is any arbitrary time. Then again, summation of all the xi square. I is number of the record. So I is equal to 1 to n, n goes to large. the mean square value. Mean square, which is really the mean square with respect to 0. This is what really, if I give a more detail that I could say. And another one before the autocorrelation, another one is variance. The variance. It's gonna all coming back a couple more times, then you would know the variance. You heard about it? Anybody heard about the variance? What's the variance? You heard about the standard deviation? Yes, I heard about the standard deviation. Standard deviation. What does it do? Standard deviation over mean square value. Standard deviation. So standard deviation square is equal to the variance, you see? And when you look at the mean square value, that mean square value is a measure of the spread of population about the 0. This is first understanding the term. The variance or the standard deviation is a spread of the population about the mean of the populations. You see the differences? So I didn't talk the probability function yet, but I'll just keep talking, then it will register in your brain. Okay, something new coming in, but I know that probability in engineering sense is a chance. Okay, what's the chance to win the 100 million lotto? Almost none, right? Probability or chance equal. So this is something like x here. Then this mean square or RMS value. If you plot this guy, you could have this, which means mean is about 0. I could fit something like this probability density function. Then I could say, oh, this is spread of population. Population, that means it's simply the data, measured data. And as we look at it, then this is mean is equal to 0 right here. But sometimes spread is not about the 0. It could be something like this. But the probability density function is very close to a normal distribution. It's symmetric about the middle. So in this case, this is a mean, something like x here. This is, as you look at the mean here, is spread about the mean, is about the symmetric. Okay, that situation, then I could say use the variance. Variance is really spread of the population about the mean value. So here you could say the variance is standard deviation square, which is equal to e to the x minus mu x square. this is x squared in this case. Should have, this is okay. So you should have this spread is about the mean. This spread is about x is equal to 0. This case is about the mean here. So variance is another good parameter. This is second parameter. This is a third parameters. Okay. Some people use another name, kind of the word for definition. This is second central moment. Just simply, as of right now, think as just a name. The central means that it's not 0. This portion, this is take away this mean from x, and the spread is measured about the mean. Okay. So if I just write in this case here, it's very close to the second one. It's a limit n goes to infinity 1 over n. So it's gonna be n is equal to 1 to n, and which is xt I minus mu x squared. Take away the mean, because I want to really see the probability functions when I give a shift to the mean value. So these three are kind of basic parameters, remember. Mean value and mean square value, or RMS value, and the third is the variance or standard deviation square. When you hear about the standard deviation or mean square or RMS value, that is giving the spread of the population. Spread is probability density function. Some are spread. If I just take average, it's gonna go like this, and this is px. Some spread is like this. If I have, let's say, the material is a steel material, then we conduct the testing just by the pull testing. As you pull it, the yield stress of the specimen, you can plot the x as the yield stress. Yield stress in the materials mechanics, you use also sigma y. Don't confuse sigma y as the standard deviations. So you just get 10 of them, 100 of them, 1,000 conductor testing. Then some specimen you have, when you plot it, it's going to be like this. Some specimen is going to be spread bad. Some batch or some steel material made by one company, A company, is like this. Let's say another company is spread is like this. Then which product do you want to buy? A or B? If you do not answer correctly, you know what I'm talking about. B is what you're going to buy. Because the spread is very narrow, which is good. If the spread is like this, A, terrible. Yield stress is sometimes, like a tensile, and this is compressive testing. If it's spread like this, yield stress is all over. Bad. But here is concentrate to the center, which is far better. So this is the one you will pick. This is not good. Okay? So we should have a society to produce like a B quality of material. So that's what these three parameters, mean and mean square or root mean square, RMS. Another measure is variance, which is also standard deviation square. And over here, another parameters I introduce here. This is called autocorrelation function. This autocorrelation function you can include as one additional the statistical parameter, okay, which is R x is equal to e to the x t plus tau. It's a time delay. This is called the time delay. Delay function. So when you get down to certain area, I'm going to talk more. The data are said to be stationary if the result remain constant with the changes in the time t1. For stationary data, the result can be computed from the appropriate ensemble at time t1. It's very simple. So over here, you are going to take the record of a peak at any arbitrary time. If it's all same, I can just pick out a time t1, then get that point, peak point, and take a measure, take a mean value, calculate the mean value. Then you take another point and compute the mean value. If it's the same, then you can call the process is stationary. Just the mean? No. Mean square value? Variance. At least 3 you have to compute. Then if that statistical parameters are same, pick out 2 or 3 different time points, calculate. If it's all same, then stationary process. Then very easy to handle. Then one more. Stationary. So when you get the signature, if it looks like a different, then you can compute the statistical parameters, right? Statistical parameters. Then if it's all same at different time, then it's very easy to handle. Use a particular statistical law, then you can quantify the material or processes. Oh, this is good, this is bad, this is doable, the vice versa. But one more is called algorithmic process. One is algorithmic processes. algorithm process is a subset of stationary process. So a stationary process should be right here. This is subset. If the signature is algorithmic process, oh, surely that belongs to a stationary process. Okay. What does it mean, algorithmic process? Now you know the stationary process, but algorithmic process is okay. I'm going to just try out. I'm going to take just one sample function, then I'll compute the typical statistical parameters, and I'm going to take this guy, just one sample function, then compute the statistical parameters. When I say statistical parameters, mean, standard deviation, RMS. Okay? Then if this is all same as the statistical parameter, that you compute at any arbitrarily the time point. You follow me? If it's all same, then you can say that this ensemble is algorithmic process. So simple, that situation. You know, so if it's a stationary process, you pick any arbitrary time, any. Then you compute the statistical parameters is all same. Oh, then that's a stationary process. But now, one more step down, pick out each individual random record, each individual random record. Then you can compute the average, right? This is collection of many points, right? Right? You can say every delta t. You set the delta t every second, for example. Then you get the set of amplitude point. Then you can compute the mean and standard deviation and RMS value. Then you compute the same way one history, one record, to compute the same statistical parameters. Then if it's all same, then that's called algorithmic process. Mostly, about 80%, I can say, maybe more, belong to the algorithmic process. God is so generous, you know. So that's what happened. You follow me? Algorithmic process, stationary process, which is algorithmic data. Algorithmic data, before it was not summation, the integration of 0 to time t, integration, so it's one record at a time, up to time t here, you take the mean, standard deviations, RMS. So this is a mean at time t1, any arbitrary time, this is equal to mu x. Mu x, this is that, which is one record. This is a mean of one record. Follow me? Yeah. So Che, you have a class here? You have a class? No. We almost finished. And this is mean square value for the one record. T goes infinity. That's a theoretical kind of expression. T never goes infinity. You never we have a finite life. So that's what the beauty in engineering. We can live with slight differences. We can live with sometimes a 4% error, sometimes a 5–10% error. So that's what the approximation come into picture. Physicist really wants to have 0.00001% error. Some science requires that, but engineer, we can tolerate 5% error. So this is that, and this is one record from 0 to t for this. Okay, this is 7 o'clock. I'll stop right here. And one more, algorithmic. Didn't go through myself to prove algorithmic theorem. Algorithmic theorem, this is like a sufficient condition, and the mathematician's expression, this is Dr. Van Datz, his mathematician. So it converge, Rxx eventually converge to mu x squared. In the time domain record, it converged to this. Then you can claim that that's algorithmic process. So, but for engineers, the statistical parameters I suggest you compute, that's enough to declare whether the signature is algorithmic, stationaries, and all that. That's what you would do. Okay, well, thank you for coming tonight, and I can tell already 3 missed the class. I know why. 2 from STX, and 1 is Yunsuk. So that's what happened. And Jabam, I don't know what happened to him. He's working in industry, so that's what happened. Okay.